Hey there, this is a guided practice 24. We're working on section 11.5 on alternating series test. Remember that for alternating series test, we need to show two things. Number one, we need to show that it is decreasing. The sequence is decreasing. And number two, we need to show that the limit as n goes to infinity of bn equals 0. Okay, if not, then it diverges. So determine whether the series converges or diverges. So we're taking a look at number one. We have the negative 1 to the n. That's the alternating piece. So my bn here is the part without that. So that's 1 over n to the 1/2. And so first of all, we want to show that it is decreasing. So part 1, we want to show that bn is greater than or equal to bn plus 1. And that's 1 over the square root of n is greater than or equal to 1 over the square root of n plus 1. Multiply both sides by both denominators, and you're going to get square root of n plus 1. It's greater than or equal to square root of n. And you can square both sides here and get n plus 1 is greater than or equal to n. And that tells you that 1 is greater than or equal to 0. So it is, in fact, decreasing. Number 2, we want to show that the limit as n goes to infinity of bn is equal to 0. So we take the limit as n goes to infinity of 1 over n to the 1/2. That's 1 over infinity, which turns out to be 0. Which means that it converges by the alternating series test. Okay, which is what we want. Okay. Number 2, same kind of thing. We want to show both things. So number 1, we want to show that it's decreasing. So we want to show that bn is greater than or equal to bn plus 1. In this case, your bn, if you take away the negative 1 to the n, that's n over ln n. So you have n over ln n greater than or equal to n plus 1 over the natural log of n plus 1. Okay, cross multiply here. You've got n times the natural log of n plus 1 greater than or equal to n times the natural log of n plus the natural log of n. And let's see. If we divide through, let's see. Let's subtract over the n term. So let's make it n times the natural log of n plus 1 greater than or equal to, minus n natural log of n greater than or equal to natural log of n. Let's take the n out, and then when you have two natural logs, you can split that. So this is the natural log of n plus 1 over n, greater than or equal to the natural log of n. Let's see, what do we have going on here? This one's a little bit tricky because the way that natural logs work. Trying to think of one thing, sorry. Okay. Let's see here. So now we have n natural log of 1 plus 1 over n is greater than or equal to the natural log of n. This is tricky. Let's take a look at the graph of this one. This one's hard to prove. Let's take a look at the graph. Okay, so we want to plot n divided by, oops, keep hitting the wrong button, natural log of n. Nope, it didn't like that. Let's try this. X divided by ln of x. Let's see what happens. Okay, and now you can see that when we're greater than 1, this does, in fact, decrease. It gets a little bit tricky to prove that. I'm getting into some algebra blocks here. So I'll have to take a look at that one. And I'll get back to you with the proof on that one. In the meantime, we can look at the graph that shows it's decreasing. Number 2, we want to look at the limit as n goes to infinity of Bn, and we want to show that that's 0. In this case, the limit as n goes to infinity of n over the natural log of n by L'Hopital's rule, because this is infinity over infinity. This is the limit as n goes to infinity of 1 over n. And 1 over n is just the limit as n goes to infinity of n, which is infinity, which means this diverges. Okay, so that one diverges by AST. Okay, so it actually doesn't even matter whether or not it decreases, because our limit doesn't exist. Our limit goes to infinity. All right, last but not least, let's take this one. We want to show both. Your Bn, by the way, here is e to the negative n, 1 over n, sorry, e to the 1 over n, all over n. And we want to show that it's decreasing, so e to the 1 over n is greater than or equal to e to the 1 over n minus n plus 1, all over n plus 1. We also want to show that the limit as n goes to the infinity of e to the 1 over n is 0. Or sorry, let me just put the Bn in here. This is what we're trying to show. So let's look at it. The limit as n goes to infinity of e to the 1 over n. Where does this go? Okay, well, if you plug in infinity, 1 over infinity is 0. E to the 0 is 1. So this is 1 over infinity, which is 0. So it works in terms of the decreasing situation. Okay, we might get ourselves into some weird algebra here. Okay, let's see if what we can do with this one. Let's cross multiply. So n plus 1, e to the 1 over n, greater than or equal to e to the 1 over n plus 1 times n. And this is n e to the 1 over n plus e to the 1 over n, greater than or equal to e to the 1 over n plus 1 times n. Okay. Again, the algebra gets a little bit tricky here. Let's maybe if we go back here and take the natural log of both sides. If we take the natural log of both sides, then we have the natural log of n plus 1 plus, right, this is like this. And when you have a product, you can split the natural logs using addition. The natural log of e to the 1 over n. So this is the natural log of n plus 1 plus 1 over n. And we're saying that that's bigger than the natural log of n plus the natural log of e to the 1 over n plus 1. And we get the natural log of n plus 1 over n, greater than or equal to the natural log of n plus, again, the ln and e cancel out, and we get 1 over n plus 1. Okay, now let's compare the two individually. Let's look at these two. ln is an increasing function, right? Its slope is 1 over n, and that's positive for all positive values of x. So we know that the ln increases. So that means that this is true, right? So we know for sure that the ln of n plus 1 is greater than or equal to the ln of n. And then if we take a look at this one, 1 over n we know is decreasing as well, right? We can show that 1 over n is greater than or equal to 1 over n plus 1. If you cross multiply, you have n plus 1 is greater than or equal to n. Subtract the n's and 1 is greater than 0. So that is true. So if you're adding something larger on the left to something that's already bigger, then that's going to be bigger than something smaller added to something smaller. So we can get at it that way. Okay. And so therefore it's decreasing. And because the limit is also equal to 0, then this converges. by AST. Likely we could do something similar up here if we took the E of both sides. We would likely run into the same kind of thing. I'll try to show you that too in a little bit. All right, now here's some examples. We're going to approximate the sum of the series to 4 decimal places. All right, so what we want to do here is we want to start adding on terms until we want to be correct to 4 decimal places. So we were looking for a term. We're looking for a BN that is less than or equal to 0.0001. When that happens, I can stop at the term before that, okay? That's what the estimation theorem says. So let's see. When I plug in 1, I'm going to start out negative over 2 factorial, so that's 1/2. When you plug in 2, and there's no parentheses around the 2n, so I'm assuming that this is sum n equals 1 to infinity, negative 1 to the n, and 2 times n factorial, okay? So when I plug in 2, the top number is squared, so it's positive. The bottom number is 2 times 2 factorial, so that's 4. And then I'm going to alternate signs. So the 1 stays up top. 3 factorial is 6 times 2 is 12. Then plus 1 over 4 factorial is 24 times 2 is 48. Minus 5 factorial is 120 times 2 is 240. Plus 1 over, the next term is 720. 720 doubled is 1440. Let's check that one. 1 over 1440 is 0.00069, so not small enough for us yet. So minus 1 over let's see, 720 times 7 times 2. So that gives us 10080. And then if I divide that one out, I get this term is 0.0000, 4 zeros, and then 99. And so that is the term that we're looking for. So we can say that 1, 2, 3, 4, 5, 6, 7. So B7 is less than or equal to 0.00001. Nope. 01. And so then S6 is what will give me an estimate. So I'm just taking the first 6. So that's negative 1/2 plus 1/4 minus 1/12 plus 1 over 48 minus 1 over 240 plus 1 over 1440. And I can stop there with those 6 terms. So let's see what that comes out to be. And I get negative 0.3160. It's rounded to the 4th decimal place. Let's do one more of those. Okay, so we want to think this is alternating. So we're going to plug in values. And again, we are looking for the BN that gives us a number less than 0.0001. Okay, that's correct to 4 decimal places. So we start out with, when you plug in 1, this starts out positive, and 1 to the 6th is 1. And then we're going to go to negative. So we're going to alternate. 1 over 2 to the 6th is 64. 3 to the 6th is 729. Oops. We're alternating sign. The top tells us to alternate the signs. 4 to the 6th is 1 over 4096. That one's not quite small enough. If I check that one, it's 0.00024. I need 4 zeros in there to make it correct up to 4 decimal places. That was my 4th term, so 5 to the 6th is going to be plus 1 over 15,625. And that turns out to be 0.12364. So that's the one that we want. And that is 1, 2, 3, 4, fifth term. So B5 is less than or equal to 0.0001. And that tells me that my S4 is accurate enough. So 1 minus 1 over 64 plus 1 over 729 minus 1 over 4096. So if we find that, that's 1 minus. And we end up with 0.9855 as our estimate. And then lastly, last thing we want to show is determine whether a series is absolutely convergent, conditionally convergent, or divergent. And so remember that we're looking for whether the absolute value of the series converges. So you're looking at n equals 1 to infinity, the absolute value of negative 1 to the n over n to the fourth. And that's just the series n equals 1 to infinity of 1 over n to the fourth, right? You're removing the piece that alternates. This is a p-series where p is equal to 4, which is greater than 1, which just means it converges. And if the absolute value converges, then we would say it is absolutely convergent. The second one, if we look at the absolute value here, n equals 1 to infinity, absolute value of our an, that's n to the 2/3. And so that's just n equals 1 to infinity of 1 over n to the 2/3. This is also a p-series where our p is equal to 2/3 and our p is less than 1, and that tells us that it diverges. Okay, so that tells us that it's not absolutely convergent, but it doesn't tell us that whether it's conditionally convergent or whether it's divergent. So in order to take a look at whether it is conditionally convergent, we need to look at the original series. So the one that alternates. And what we need to do there is we need to show two things. You need to show, one, that it is decreasing. And two, you need to show that it is the limit as n goes to infinity of your bn is equal to 0. All right, I'm going to do the second part first because it's quicker. Your bn here is 1 over n to the 2/3. So if we look at this is the limit as n goes to infinity of 1 over n to the 2/3. And that's 1 over infinity, which is 0. So that works. Then we have to show that it's decreasing. You just show that bn is greater than or equal to bn plus 1. So we'll try that. So we've got 1 over n to the 2/3 is greater than or equal to 1 over n plus 1 to the 2/3. Okay, multiply both sides to get rid of your denominators. That gives you n plus 1 to the 2/3 is greater than or equal to n to the 2/3. If you raise both sides to the 3/2 power, that gives you n plus 1 is greater than or equal to n. Subtract your n's and 1 is greater than or equal to 0, so that's true. The other way that you can show that something is decreasing is by showing that its derivative is always positive for n greater than 1. So we could look at the derivative here. Bn prime is 2/3 n to the negative 1/3. And this is 2 over 3 cube root of n. And when you're plugging in positive n's, the cube root is positive, and 2 over 3, that's all going to be positive. So this is greater than 0, which tells you that it's increased. I apologize. Let's get our powers correct before we do this. Your bn is equal to n to the negative 2/3. When you take the derivative, that's negative 2/3 times n to the negative 5/3. So this is negative 2 over 3 n to the 5/3. You're plugging positive numbers in for n, so that you're going to get positive numbers back, but the negative on top shows you that this is less than 0, which means it's decreasing. for all n that are greater than 0. So 2 ways to show that it's decreasing. Therefore, it is convergent by AST. So the original series is convergent, but the absolute value is divergent. This together tells you that it's conditionally convergent.